Today, I'd like to bend your ear on how to make better decision making using data and analytics, specifically linear and mathematical programming use cases. The idea here is that oftentimes when we make decisions, we use our intuition, but I'm here to prove why numbers and intuition don't always add up. And then when you're trying to solve complex problems, mechanisms, and a process in which you can lay that out mathematically or really through solvers to achieve that end state. We're not going to go through any proofs. We're not going to go through any calculations. But in the end, if you want to have a future discussion on this, please reach out and we can chat about that. But first, we need to understand numbers and intuition. They don't always make sense. I'll use this by illustrating a old TV show called Let's Make a Deal. The host of that show was called Monty Hall, and they call this the Monty Hall problem. If you haven't seen it, it was essentially a bunch of contestants dressed in wacky costumes that would come up, and then Monty Hall would introduce different prizes. They would say, "Hey, I want to open this door or that door," and he'd essentially coordinate that. So let's say that the contestant came up and they have the option to win a new kitchen, a brand new Corvette, or potentially the rough one in the batch was the set of hay bales. Monty Hall asks the contestant, "Which door would you like?" And the contestant looks and says, "I want to open door number 2." So in that door, they have a brand new kitchen set. The guest is ecstatic, very happy that they won, but then there's a twist. So Money Hall looks at the guests and says, "If you give me back that kitchen set, I will give you another opportunity to open the doors." So the contestant has door number 1 and door number 3 left. Essentially, the contestant thinks it's a 50-50 shot of winning the grand prize of the Corvette. This is where we'll pause for just one moment. Is it a 50-50 shot? Because we got to think about the problem as a whole. Really, they have a 66% chance of winning the grand prize because 2 out of 3 doors they know. That's the entire crux of this equation. That most people would think that's a 50-50 solution, but in reality, it's a 66% chance of winning, and that numbers and intuition might not always be inclusive of one another. So if you guessed, hey, door number 3, you won an imaginary Corvette. But really the takeaway here is the idea that numbers and intuition might not be as intuitive as we once thought. So how do we make them intuitive, and how do we solve these types of problems? That's where mathematics and linear programming come into play. So mathematical programming is, and this definition is from Cliff Ragsdale from the Spreadsheets Modeling and Decision Analysis sheet, where I learned quite a bit of this material, is trying to find the optimal solution using limited resources to achieve some objective, also known as optimization. And we're going to not make it a buzzword. We're going to actually show how to put these resources to use in an actual demonstration. You have 3 core areas: decisions, constraints, and an objective that you want to achieve. These decisions that you look at are essentially the knobs on the wall that you're turning to achieve that optimal solution. If you're running a small t-shirt company, the decision is how many t-shirts and how many sweatshirts do I need to produce to maximize my given profit. Constraints are essentially resource constraints that we have. You only have so many employees. Potentially, this is a small shop. You have 2 employees, so 80 hours or 90 hours is your total number of hours that can be worked. Maybe you have only so many materials and you have so many yards of fabric. That's another potential constraint. And it's often expressed as an inequality, so less than or equal to, greater than or equal to, or equal to solution. Every time we add a constraint, the feasible solution is minimized as well. And then the objective is really what we're trying to solve. And in linear programming problems, it's typically a minimum or a maximum type of solution. Think about this. I want to find the optimal inputs so I can minimize my total cost. Or I want to find the optimal inputs based on my constraints to maximize my profit. Both very, very important aspects of a business. And I just want to note that I'm going over the essential aspects of linear programming. They get very, very complex in 3-dimensional, 4-dimensional, 5-dimensional spaces. Use these in the real world, and at the end of the day, while the complexity may scale, you've got to understand that decisions, constraints, and objectives are in every single one of these problems in just a more complex set of instructions. But I'm a visual learner myself. So let's take all of these inputs and actually put a graphic to it. And we'll start with the X and the Y, the X and the Y axis. And what our objective is going to be is I want to maximize profit. What does that look like on a graph? So first and foremost, if we have no constraints, no inputs or anything, we sort of have an infinite number of a feasible region. I probably should have made the graph a little bit different, but that line there is essentially representing the linear edge of the feasible region, which is where our solution will lie. Now, there are options for the feasible answer to be inside the shaded area. Those are what we call nonlinear programming equations, and we're not going to solve for those today. We're just going to solve for the linear program, which means the answer lies on this line. All proofs and mathematics behind this, we can go into a deeper conversation in the future on, but really I'm just trying to explain the fundamental building blocks as well as how to do this in a solver formula. The next area that we have are the variables, in this case, shirts and sweatshirts for our small t-shirt company. We can only produce so many of them. Finally, we add in the constraints, which then minimize the feasible region that we can solve for. So if we're solving for the line, the constraints essentially chop off this section and this section. So if the feasible solution was over here, now it has to be within this line here. And that's annotated by the green shaded area on the chart now. Now I'm going to go to the bottom of this chart, and then we'll go up into the actual demonstration purposes. So there's different types of common solvers that are available to you today at no cost. You might say I could use AI to solve these types of problems, and I'd say you'd probably be incorrect. AI has a difficulty when you try to lay this many variables in and actually solve the output. At least today, it's very difficult for it to work through these types of problems. On the data continuum, prescriptive problems are the hardest to solve. Thankfully, we have things like Solver, Pyomo, Gurobi, and Pulp to help achieve that. Solver is an Excel add-in. Pyomo and Pulp are free Python packaging, and Gurobi is a licensed solver package. As these get more and more complex, they become much more difficult to articulate, which is why AI has difficulty in setting up the given problem. So let's take a problem statement and actually build one. Let's say that we are an apparel business creating two types of products, shirts and sweatshirts. We need to know the optimal number of each one of these to produce given the constraints listed below. One shirt requires an hour of work and a sweatshirt's 3 hours. We only have 90 hours of total available labor. We must produce at least 20 shirts and 10 sweatshirts. Each shirt uses 1 yard of fabric, and each sweatshirt uses 2 yards of fabric with a total of only 250 yards of fabric available. And then the profit margins for each one is $15 per shirt and $25 per sweatshirt. So how do we optimize that profit? Let's go ahead and set up the equation. So what we'll do is lay in what that problem statement is first. I kind of already have it here. I pasted it earlier. I like to do that so I can flip back and forth between each of the areas. And then we'll begin setting up the actual problem statement. So first and foremost, we have so many shirts and we have so many sweatshirts. These are what we're trying to optimize for. We have a number that we need to produce for each of these. I like to put the variables, if we think about those knobs that we're turning, I like to turn those blue. The reason why is I was taught this way, and it's the easiest way for me to sort of understand what each of those constraints, variables, and objectives are doing. We are trying to make, we know what the profit for each of these are. And in this case, it's $15 and $25. Let's just make it a new number sign. And then we have a demand that we need to fulfill, at least fulfill which is 20 shirts and 10 sweatshirts. We have constraints as well. And on these constraints, we have resources as one constraint. And then I like to repeat, not resources, we have the resources as sort of the column header. And I like to repeat what the variables that we're solving for, just to make it easier to solve. So shirts and sweatshirts. And our resource constraints were hours and fabric. And then finally, we need to be able to annotate what we use and then how many resources we have available to us. Our available resources, we said, were 90 hours of labor and 250 yards of fabric. We have the hours it takes to make a shirt is 1, and then 3 hours for a given sweatshirt. We have 1 yard of fabric per shirt and 2 yards of fabric per sweatshirt. Our total profit, we'll just annotate over here as a green for money. And that's what we're trying to optimize, is the total profit. Additionally, those constraints I like to highlight in yellow. Like I said, I was taught to do these problems in this way when I'm working with spreadsheets. Now we have the sort of the layout or the framework of what we want our problem to say. Now we have to fill it in with information. So to do that, we need to understand what's the total profit equal. Well, total profit equals this times this plus this times that. You can do that with a formula called equal sum product. So this array times this array will give us a total profit. And I like to test it just to make sure it's working properly, and it is. Likewise, equals sum product to solve what you use based on what the optimizer is going to solve for. We're going to choose what is selected in the optimizer. We're going to multiply it by the number of hours. Then we'll do the same thing for the other resource. I like to test this as well, just to make sure it's properly allocating. Yes, it is. So now we've got our problem set up. Pretty basic, pretty simple. But the next phase is where the magic really happens in the optimizer. You can go to Data and you go to Solver. If you don't have Solver underneath your Analytical tab, all that you have to do is you go to File, Options, Add-ins, find Solver, and add it in. You can also use Google to search the specific steps if that didn't work for your system and your constraints. Now that we have this, we'll go ahead and go into Solver. A window will pop up, and it's going to ask you, what is your objective that we're solving for? Well, we want to find what our maximum profit is. We set the cell where the maximum solution is to max. And those variables or knobs that we're turning are the blue cells. See how easy this is? And then the last piece that we have to do is define what those constraints are. So the first constraint is that we need to meet our demand, at least meet our demand. So it needs to be greater than or equal to our demand. We'll go ahead and add that one in. Then the next constraint is going to be the materials that we can use. So you can't use more materials than you have. So it needs to be less than or equal to the available materials that you have. Go ahead and hit OK. Now you can see that all the formulas are filled out in here. It's solving for nonlinear. We want to solve for linear. It would solve it for the nonlinear, but just to make things simple. And then we'll go ahead and click Solve. The program will go through and try to figure out what the solution is. We didn't get any errors. It said it found a solution where everything's optimized. You go ahead and click OK. And you can see now that to achieve your max profit of $1,150, what you need to do is you need to create 60 shirts and 10 sweatshirts. You'll use all of your hours of labor while also not using all of your yards of fabric. I'll show you one more thing. Let's say our fabric was at 20 yards. We go to Solver and we try to solve it for that. We're going to get an error. That error looks like this red check mark, and it says that it can't find a feasible solution. But it'll show you what it kind of does, so you can understand where those feasibility issues reside in your plan. And right here it resides in this use versus available software or yards of fabric. So thank you very much for sitting through this presentation, learning something about linear programming, and letting me explain the fundamental concepts. Like I said myself, I've worked on these quite a bit in the past, done much more complicated problems than this, but I think this is a good example to sort of dip your toes into how you can use linear programming for better decision making, and essentially understanding that intuition and numbers don't always mix, but there are ways and tools and mechanisms to help make that easier. If you want to begin to use this yourself, Excel Solver is the gateway, and then more advanced Pyomo and Pulp, and ultimately Gurobi options are available to yourself and or the business that you're working with. Thank you again, and have a great night.